So this is Math 150, Section 1. Let's call it Lecture 34. Sounds right. Yeah, it's got to be mod 1. It's going to be 1 when you divide by 3 as the remainder. So we're in the home stretch. What I want to do today is talk about why Taylor series expansions are accurate, talk a little bit about what a Taylor series expansion would be in several variables, and then go and see some applications. So I had mentioned last time that the main ingredient in the proof is going to be the mean value theorem. Let's quickly review. So a Taylor series, so we'll say maybe fn of x would be the sum, k goes from 0 to n, of the kth derivative at 0 divided by k factorial times x to the k. And this is the Taylor series about the point 0. If I wanted to be about the point A, I would have the derivative at A, and then I would have x minus a to the k. This will be a Taylor series of degree n, because n is the highest term. And so we'll look at the error, and I'll call it, h of n will be f of x minus fn of x. The reason I don't want to use e is we use e for the exponential, so I don't want to use e for my error term. And so the idea is we want to see how small is this. So it should be small if x is close to 0. So that means we're very close to the point we're expanding by. But what we really need to do is we need to explain what we mean by close. Close relative to what? And it's got to be close relative to x. So in fact, we want f of x minus f n of x, our approximation, divided by x to the n to be small. That would be a really good approximation. So for instance, if you think of x as 1/10, if we take a degree 5 expansion, then this should be so small that even when we divide by x to the 5th, 1/10 to the 5th, it's small. Well, that makes sense. If you look at this, if x is small, the higher powers of x are very, very small corrections. The main term is going to be f of 0. And then the first term is going to be most of the correction. And then the term after that is going to be most of the remaining correction. And the smaller x is, the more you're dominated by that constant term. The further out you go, the more the other terms are going to matter. And the worse you might expect your fit to be. So we want to show that not only is it small, but it's small relative to x to the n. And that's the right scale to be looking at. Because the last correction that we add, the final term, is of size x to the n. So when we're trying to see how large is it, that's the correct scale to look at. Okay, so let's study h of n. This should be h of x. Let's study h of x. Can anybody give me a good point to evaluate h of x at? So I've spent this morning jogging to places on Route 2, jogging to the bank, jogging here. I'm tired. Help me out. What would be a good place to evaluate h at?
0.
0. So h of 0 is f of 0 minus fn of 0. But when you put in x equals 0, the only term that survives is the first piece. Right? Because fn of x is f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared. So when I put in 0, everything vanishes but that. So we get h of 0 is 0. So really, h of x is the same as h of x minus h of 0. Now, what theorem have I told you should have on your mind? Mean value. How can I use mean value here? I've got h of x minus h of 0. According to the mean value theorem, what does that equal? So this is one of the things you should have on instant recall. It's h prime at some intermediate point times x minus 0, where c1 is in the interval 0x. Or I don't know if x is positive or negative, so. Normally we use the letter C. Why do you think I'm calling it C1?
Maybe there could be like multiple possible like constants, like if you're in like multiple dimensions or something.
But we're in only one dimension right now. What if I tell you somebody survived their first heart attack? What can you probably conclude? Yes?
They had more than one.
They probably had more than one if I'm using the phrase first. In high school, one of my friends said, so-and-so had 2 heart attacks, he survived the first. We thought it was a little bit unnecessary to say he survived the first once you mentioned that there were 2 heart attacks. But when you hear the phrase first, you often think there's a second, there's a third. Not always. It's perfectly fine to say first without there being a second. But you often want to think that. I'm using the C1, I've got one derivative here. I have something where I'm looking at n derivatives. I'm probably going to be differentiating many, many times. And each time I differentiate, I'm going to use the mean value theorem again. So I'm going to put subscripts to let me know which time in the differentiation is this. So this is equal to h prime at C1 times x minus 0. Now what's nice about this is x minus 0 is small. X is supposed to be small. And now we just have h prime of C1. Okay, well, h prime of x, well, h prime is just the derivative of h of x. H of x is f minus fn. So it's going to be f prime of x minus this derivative. So it'll become minus f prime of 0 minus f double prime of 0 x minus f triple prime of 0 over 2 factorial, because the 3 came down, x squared. So that's h prime of x. Is everybody comfortable? And this is what h prime of x is. Okay. What would be a really good point to evaluate h prime of x at?
0.
0. And so if you look at h prime of 0, it's going to be f prime of 0 minus f prime of 0. Everything else is 0. So we get h prime of 0 is 0. This is the shampoo method of mathematics. Lather, rinse, repeat, lather, rinse, repeat. Keep doing the same thing again and again. Whenever you have something that's 0, you can subtract it off. And so now we know h of x is h prime of c1 times x, which is h prime of c1 minus h prime of 0 times x. What can we do for h prime of c1 minus h prime of 0? Mean value. And so this will be h double prime of c2, and then we'll have c1 minus 0 times x, where c2 is between 0 and c1. So to recap what we have so far, we have h of x is equal to h double prime at some special point c2, c1 times x, where the absolute value of c2 is less equal to the absolute value of c1 is less equal to the absolute value of x. Let's do it again. H of x, if we do the argument again, what do you think h double prime of, so if we take the derivative, if we look at h triple prime of 0, what do you think h triple prime of 0 will be? So what should h triple prime of 0 be?
H triple prime of c.
No, h triple prime of 0.
Oh, 0.
So what should h triple prime of 0 be? So h of 0 was 0, h prime of 0 was 0. Oh, did I skip h double prime? I'm sorry, h double prime. What should h double prime of 0 be? 0. And h triple prime of 0. All the way up to the nth derivative of h at 0 should be 0, because we've chosen our polynomial to match the first n derivatives. So when we do this again, we'll get h of x is h triple prime of c2 minus h triple prime of 0 times I think c1 no, sorry, it's h double prime of C2 minus h double prime of 0. We just subtracted h double prime of 0. And then that's going to be h triple prime at C3 times C2, C1 times x. And we can keep going, and we'll get h of x is the nth derivative at some point Cn times Cn minus 1, Cn minus 2, C1 times x. And then if our function is differentiable n plus 1 times, then we get h of x is the n plus first derivative at some point Cn plus 1 times Cn, Cn minus 1, C1 times x. Or the absolute value of h of x is less than or equal to the maximum of c less than or equal to the absolute value of x of the nth plus first derivative of h at c, absolute value, times x to the n plus 1 power. So if our function is differentiable n plus 1 times, when the dust settles, let's do a worst case analysis. Worst case analysis, let's assume this point Cn plus 1 is at the worst possible place it could be for us, where this function, the n plus first derivative of h, is as large as possible. And then let's assume all of these c's are as large as possible. The largest they could be is x. It is unlikely that every single time they will be as large as x. But worst case scenario, that would be what happens. And so this should be an absolute value of x. And so this would be a bound on the error term. Now one thing that's a little bit annoying is we have an h here. We want the error in terms of our original function f. But if we differentiate h n plus 1 times, let's look and see what was h. H was f minus fn. F is a polynomial of degree n. If we differentiate a polynomial of degree n, n plus 1 times, what do we get? So if you differentiate a quadratic 3 times, what do you get? 0. If you differentiate a cubic 4 times, what do you get? 0. We differentiate this n plus 1 times. The highest term is an x to the n. N plus 1 derivatives killed this. So when we differentiate n plus 1 times, the derivative of fn is 0, so the n plus first derivative of h is just the n plus first derivative of f. That's really good because we want to express our error in terms of the function we're given. And so we can actually replace the h with an f. And this is our error. So the error is at most the maximum value of the n plus first derivative times x to the n plus 1. If you are willing to do a little bit more work, you can get a better error. You can actually get either an n or an n plus 1 factorial down in the denominator. If n is large, that's a huge savings. But n is fixed. And x is shrinking. So the thing that really matters is not whether or not there's an extra n factorial at the bottom. It's how does this depend on x? And that's why, if you want, I will send you a link where you can see the slightly more rigorous proof that gets you a slightly better result. But this result is enough to show us that the difference, the error, is of a higher order of x if we have one more derivative in the bank. So this is a good description of why the Taylor series does so well, that your error is smaller than the last term in your expansion. And so if x is 1 over 100, that gives you some confidence as to how accurately are you estimating things. Okay, any questions about this proof? So I really like this result. It's another great application of the mean value theorem. And again, the mean value theorem is non-constructive. It just says there exists a point. A lot of times in life, it's not enough to know that there exists something. You want to know, where is it? How can I use it? Well, we actually can answer how we can use it without knowing where it is. We can do a worst case scenario, and we can say, well, worst case scenario, all of these are the size of x. Then you could try to argue, well, do we really think that that's the worst case scenario? Are there some functions where this could actually happen? For a generic function, how often each of these may be half the size of the previous versus twice? I don't know. You could start trying to play games like this to get a sense of how much more accuracy do you have. I will risk asking this question. Does anybody remember Simpson's rule from calculus? Did anybody do this with trapezoids and finding areas under curves? There's some ways to numerically approximate integrals that are actually more accurate than you might expect because the next term in the expansion turns out to be 0, so it's accurate to 1 degree higher than you would expect. Things like this do happen, and it's worth analyzing just how good is your result. Okay, so now that we have done this, it is now time to shift gears and talk a little bit rigorously about multivariable Taylor series expansions. And this becomes a nice way to review some of the stuff from chapter 11. So as a rule of thumb, we always want to take something we know and generalize it and see how else can we write it, how else can we push it. So one dimension, we have fn of x is f of 0 plus f prime of 0 x plus f double prime of 0 over 2 factorial x squared. Now let's say we have we can't choose n dimensions, we'll say m dimensions. We have f of x as a vector is f of x1, x2, xn. So I have a function of n variables, and I want to calculate the Taylor series expansion. One way you could approach this is fix all but one variable. Let's say I fix variables x1 through xn minus 1. I now have a function of one variable. What can I do with a function of one variable? I can Taylor series expand it. But then my coefficients would not be constants, they'd be functions of x1 through xn minus 1. And I take each one of those and then I expand it. And you can keep playing this game. So that's one approach to get to a multivariable Taylor series expansion. The other is to try to guess what you think the expansion should be. So let's say we want to have a degree d Taylor series expansion. What do you think the first term should be in the Taylor series expansion? Yes?
F of x1, x2, not xn.
Well, Taylor series, where am I expanding by?
At 0.
At 0, so what should it be?
F of 0.
Yeah, f of 0. Now, what do you think the next piece should be? So that's our start. Yes?
F prime of 0.
When you say f prime, I get sad. I don't like f primes for several variables. Because when you say prime, what do you...
Gradient?
The gradient of f, at what point?
0.
At 0.
Times x, right?
What do you mean by times x?
Oh, times the vector. Oh.
So yeah, now we got to figure out what do we mean here. How do you generalize multiplication now? Any thoughts? Dot product. This is a vector. X is a vector. So we take the dot product. Okay. Anybody want to try and guess what the next term would be? Or at least how do you think the next term starts at least?
The gradient of f?
So this is called the Hessian matrix. So it's the matrix of derivatives. So its entries are d squared f dxi dxj. What should we have in front of the matrix? It's going to reduce to the one-dimensional case. So what should we weight it with a factor of 1 like we weighted this, or should it have a different factor?
1/2.
It should have a 1/2 or 1 over 2 factorial. But now I have to figure out, I have a matrix. I have to do, and I have an x squared. So it turns out, if I go x1 through xn like this, a matrix acting on a vector like this will be a vector, and then I can put the other vector like this, and basically do like a dot product. You don't want to see what comes in when you get to degree 3 and higher. You no longer want to try to write it down like this. But this is the natural interpretation of what does it mean to multiply these three numbers. I've got two vectors and a matrix. This sounds like a bad movie. How can I combine them? I can combine them with matrix acts on vector gives me vector, and then take the dot product. general way of writing this, I will take the piece of paper and just make sure I do not miswrite this, because it is very easy to drop something the wrong way. It will be the sum of the absolute value of alpha is less than equal to d. There's lots of different notations you can use. So I'll take the notation Wikipedia, d alpha of f at the point 0, and then x minus x to the alpha over alpha factorial. So this requires a lot of explanation as to what this means. So here, alpha is alpha 1, alpha 2, alpha n, and each is a non-negative integer. The absolute value of alpha is the sum of the alphas. And x to the alpha is x1 to the alpha 1, x2 to the alpha 2, xn to the alpha n. So if you think about this, this at least makes sense. That when I have a Taylor series in degree 1, I have 1x, x squared, x cubed. If I have it in two variables, I should have a 1, an x, and a y. X and the y are my only degree 2 objects. My only degree 1 objects. My degree 2 objects would be x squared, xy, and y squared. So let's do two variables. So degree 0 is just the constant term. Degree 1 is x and y. What would the degree 2 terms be? So I have just two variables, x and y. What would all the degree 2 terms be? X squared? Anything else?
xy.
And xy. Now I have xy, I also have yx. Is xy and yx different? Is x times y the same as y times x?
Yeah.
They're the same. So I actually didn't tell you what alpha factorial is. Alpha factorial is alpha 1 factorial, alpha 2 factorial, alpha n factorial. This basically takes into account all the different ways you could get a term. So when you look at this matrix of derivatives, if my function is nice, if my function is twice continuously differentiable, then d squared f dx dy is d squared f dy dx. And I'll have two matrix elements that are the same. And I'll get an xy term two different ways. And so when you expand all this out, the 2 factorial is actually going to drop for the xy term, but it will be present for the x squared and the y squared term. If I wanted to do degree 3, I would have an x cubed, an x squared y, an xy squared, and a y cubed. And so on and so on and so on. And it gets worse the more terms you have. If you're at degree 4, 5, 6, 7, you have more and more terms. The more variables you have, the worse it gets. So a lot of questions you could ask is, this is looking at all tuples of a given weight, of a degree at most d. How many are there? Turns out this is a very nice combinatorial problem. And when I teach probability, I talk about how you can, count this. We are not really going to do much with this. You just should at least be aware of this. And I want to give you a sense of why we might care about this. So I'm not going to go into much detail. I'm not going to really test you on this. If I give you something, you can basically do the cheat I told you last time. If I give you the exponential of x squared y, well, I know what the exponential of u is. So just quickly redo one example like that. And I'll talk about the application. So if I give you the exponential of x squared y, I know EU is 1 plus 1 plus u plus u squared over 2 factorial plus u cubed over 3 factorial. So e to the x squared y is 1 plus x squared y plus x to the 4th y squared over 2. And you just take u to be x squared y. So if I give you, oops, I'm not sure that would be caught. So if I just give you e to the x squared y, you can actually get that just from your knowledge of one-dimensional Taylor series. You could do the more elaborate calculations. And yeah, it's worth knowing that it exists, but at this stage in the game, I think just knowing it exists is sufficient. Let me talk to you about why this is useful for the generalization of the second derivative test. So in one dimension, we have a critical point, and this is a candidate for maximum or minimum. How do you tell if it's a maximum or minimum with the second derivative? What's the second derivative test?
You see if it's positive or negative.
Okay, so if the second derivative is positive, is it a minimum or maximum?
If it's positive, then it's a minimum.
It's a minimum. Think of your parabola y equals x squared. It's a minimum. If you take the parabola y equals negative x squared, it's a maximum. So let's imagine we're at a place where we have a critical point. So if we have a critical point, this is 0. And then how is f of x related to f of 0? It's equal to this matrix with this dot product. Strange thing going on. Right? Let's imagine we're in a special situation where the matrix is diagonal. So imagine the matrix is 2, 0, 0, 3. And I've got xy, xy. And when you multiply things out, it's 2 times x plus 0 times y is 2x. 0 times x, 3 times y is 3y. And then you get 2x squared plus 3y squared. Is this a maximum or a minimum?
Minimum.
It's a minimum. As long as xy is not 0, 0, this piece is adding a small little contribution. It's adding a small little boost. And the third degree term won't be enough to overcome this. So if you happen to have a diagonal matrix, and these are both positive, you have a minimum. What if they were both negative? So if they were both negative, instead of having a minimum, you would have maximum. You'd always take off a little. What if one is positive and one is negative? Then this is a saddle point. You're increasing in one direction, and you're decreasing in the other. And so it's neither a maximum nor a minimum. So if you have a diagonal matrix here, you're set. If you don't have a diagonal matrix, then you have to do a little bit more work, and this is where linear algebra comes into play. I'm not going to go into the details, but I might have talked about this before. If I give you an ellipse aligned with the coordinate axes, you've seen the equation of the ellipse. X over a squared plus y over b squared. If I give you an ellipse that's not aligned with the coordinate axes, what you do is you first draw new axes, and you write down the equation of the ellipse in these axes, and then you rotate those axes to the standard one. And there's ways to do that, and there's ways to convert this to a diagonal matrix in a new variable system, to do a rotation of your coordinate axes. And this is where linear algebra comes into play, and this is where you get really good second derivative tests. And it all comes from looking at this matrix, and looking at something that you'll learn later is called the eigenvalues of this matrix. This is just trying to give you a sense of what might be seen if you go into linear algebra. It's up to the professor as to whether or not they want to go and revisit multivariable calculus. This is one of the times where it's painful how we split up mathematics. Because there are so many times when it would be useful to know some linear algebra and some multivariable calculus. I took a class that was sometimes good, sometimes not so good as a freshman, where it was unified, year-long, linear and multivariable together, as well as 2 other subjects. It was intense, but you really got to see the connections, and you saved some time. The problem is if you only take one semester, you are stuck because you don't know all of linear algebra and you don't know all of multivariable calculus, and you really have no place to go. But I just wanted to end by showing you where things move, why we care so much about linear algebra, how it will help us analyze, why we care about multivariable Taylor series expansions. This gives us a generalization of the second derivative test. It helps us answer the questions of finding maxima, finding minima. All right. Any other questions? All right, so the last thing I want to do today is just revisit a problem from early in the semester, an extra credit problem. So this was trying to find the area under the normal. Unfortunately, in life, there are often different normalizations. Right? What do we call the angle coming down from the z-axis? Phi. The physicists call it theta. Does it matter what you call it? No. But if you don't know what it's being called, if you just quickly glance at a formula, you could use the formula incorrectly. So the standard normal has mean 0, variance 1. For this problem, it's a little bit more convenient to look at not the standard normal, but a slight modification. We're going to do mean 0, standard deviation 1 over square root of 2, or variance 1/2. So the density is 1 over square root of pi e to the negative x squared. And the reason we're doing it this way is this way we don't have a... Okay, doesn't really matter. You can change things, but this is the one that's been tabulated. And the cumulative distribution function, this is the probability of random variable is at most little x, is the integral from negative infinity to x of 1 over square root of pi e to the negative t squared over 2 et. Well, the first thing to note is the integral makes sense. If we integrate from negative infinity to infinity, what do we get for this probability distribution? 1. All probability distributions integrate to 1. So this is just calculating the cumulative distribution. So this is, we don't have an antiderivative for e to the negative t squared. But we have a series expansion for the exponential. So this is the integral from minus infinity to x, 1 over square root of pi, I can take that out, sum, and it goes from 0 to infinity of negative t, oh, I don't have the over 2. That's the whole reason I'm using this. Of t squared to the n over n factorial dt. And what's nice is this expansion converges for any choice of t. So I'm just expanding the exponential. What should I do to the integral sum? So I integrate the sum. Instead of integrating the sum, what should I do? What are my main techniques in multivariable calculus? I can change variables. I can change orders. So I can do the sum of the integral. So the sum, and it goes from 0 to infinity. I'll have a negative 1 to the n over n factorial square root of pi. And the integral from negative infinity to x of t to the 2n dt. Oh, well, that's an easy integral to do. So I get the sum, and it goes from 0 to infinity, negative 1 to the n over n factorial square root of pi, and then I'll get t to the 2n plus 1 over 2n plus 1, and I evaluate it at x and negative infinity. All right, what happens when I evaluate it at x and negative infinity? So what happens when I evaluate this at x and negative infinity? What do I get?
At negative infinity, you get 0.
Why do I get 0 at negative infinity? I have negative infinity to the 2n plus 1 power.
Well, that would be t to the negative infinity.
No, not t to the negative. I'm t. I evaluate t at x, and I evaluate t at negative infinity.
I thought you were evaluating n.
Nope. N is fixed, right? So what do I get when I plug in negative infinity for t, and I raise that to the 2n plus 1 power? I get negative infinity. So I would get x to the 2n plus 1 minus negative infinity. Crap. Right? I have x to the 2n plus 1 plus infinity. Now, fortunately, I have a negative 1 to the n, so I'm going to have an alternating sum of infinities. We can't interchange the orders here. And the problem is, this is the Fubini theorem. And again, this is one of the reasons I want to do this problem to review. I can only interchange if the double integral, integral sum, double sum of the absolute value is finite. If I put in absolute values, I lose the negative 1 to the n, it's going to be plus infinity. I cannot do Fubini. This is wrong. Crap. All right. Back to the drawing board. Is there any value of x where you know this integral? So this is the key observation. Can anybody give me a value of x where we know this integral? There are two answers. What's one value of x where we know the integral? 0. 0. What's the answer at 0? And the other is f of infinity is equal to 1. So let's assume x is greater than or equal to 0. I can write f of x as the integral from negative infinity to 0, 1 over square root of pi e to the negative t squared dt, plus the integral from 0 to x of 1 over square root of pi e to the negative t squared dt. What does that integral equal? One half. So I get 1/2 plus, now I'll do the sum expansion. And then I'll have the sum, n goes from 0 to infinity. I'll have negative 1 to the n over n factorial square root of pi integral from 0 to x of t to the 2n dt. Is this integral going to be okay? Yeah, because now when I put in 0, I'm just going to get 0. And so I will get 1/2 plus the sum, n goes from 0 to infinity, of negative 1 to the n over n factorial square root of pi x to the 2n plus 1 over 2n plus 1. And you can show that this sum converges for any choice of x. We know x to the n over factorial converges. So if I have x to the 2n, that's really like x squared to the n. So as a nice exercise, show that this converges for all values of x. What's also nice is we have the negative 1, so it's alternating. So it should have good convergence properties as well. No, it'll focus on this now. So this is a great series expansion. It turns out that what they do is they define what's called the error function. Error from x is the integral from negative x to x. I'm pretty sure this is how they choose to do it. Yes. Of 1 over square root of pi e to the negative t squared dt. So this is just an extremely well calculated result. This is the probability that negative x is less equal to our random variable is less equal to x. And they don't do the standard normal, they do a slightly different one, because this way we don't have that extra dividing by 2 in the exponential. If you want to convert to the normal, you can do it by a change of variables. So they just provide tables of this. So this function has been well calculated and calibrated. This is the error function. And the error function has a lot of other cousins which have been tabulated. But once you do it for this, a normal with mean 0 and standard deviation 1 over square root of 2, you can get any normal distribution by just playing some games. And it's a good exercise to say, well, if I then changed it so that it had variance 5, what would it be? But this goes back to a nice application of the series we're doing. We really need to calculate the area under normal distributions. So many things in the world are distributed normally. This is one of the reasons why it's called the normal distribution. It occurs in so many places. We want to know if things are normally distributed and I observe the following, how likely is that? Does this support the conjecture or not? And so I need to tabulate these probabilities. Unfortunately, we can't do most integration. So we need to find series expansions. And this is a very rapidly converging series expansion. What I love about this is you start off with some knowledge. I know what's going on at 0. And by using that knowledge at 0, you can bypass an alternating sum of infinities. So if you go back to the formula I crossed out, if I take the limit, if I don't put in negative infinity here, what if I put in just negative b and let negative b go up to negative infinity? As long as b is finite, this would then make sense. And I could then take the limit and that would be fine. And in some sense, you would then have that this alternating sum of infinities is converging to a half. But it would be a very, very strange alternating sum. Okay? So this gives us some explanation as to why we've spent so much time doing sequences and series in this class. You will be getting things as you continue in your careers that just can't be done in closed form. And you can do approximations, and you want to know how good is the approximation. And that's why we spent time today looking at how accurate is the Taylor series. How many terms do I need for a certain level of precision? Sometimes you may use more terms than you need just because you want to be safe. How many of you have ever ridden in an elevator? Okay. What do you notice when you get in an elevator?
Maximum weight.
Maximum weight. How accurate do you think that number is for the maximum weight? When it says 2,000 pounds, do you think 2,001 pounds will break it? No. They almost surely have a safety margin. Why? We could have more people come in the elevator. Why do they underestimate?
Because they don't want to risk getting too close.
Yeah, because if you go over, the consequence is huge. It's not a small consequence. Oh, it's just going to take us a little bit longer to get up to the 12th floor. No, we're all going to fall down and we might die. Right? Same thing when you're building bridges. If the consequence of failure is enormous, you factor in a large safety margin. But you want to know roughly how much. If you've flown airlines, how many? Albany's a wonderful airport since this is being recorded. And I love how committed airlines are to making sure flights come to and from Albany. But every now and then, not the airline's fault, act of God is what they call it. There are storms and whatnot, and planes are delayed or canceled. What do airlines do? Well, airlines actually have strategic reserves of planes. So that if some flights are delayed and can't take off on time or can't take off at all, they actually have storage areas where they have planes and crews. Why don't they have more of these? Yeah, the cost. You would rather have the airplanes flying and getting revenue from traveling than just sitting in a strategic reserve. But you need to have some safety margin in your system. Because otherwise you can have a couple of key delays at key hubs just propagate through the system and cause a nightmare. So you need to have a couple of planes that you can bring in. How many? A lot of mathematics is done to analyze situations like this, to see exactly how much of your force should you keep in reserve. How likely are you to get really close to it? How many of you have ever been bumped on an airplane? Where they give you money not to fly or to fly later? Wait, no one's ever been bumped? Have you at least heard about bumping? Okay, my favorite is my brother once wanted to fly home and see his family, and he got to the airport early and he asked, can I go on an earlier flight? And he said, sure, but that'll be so many hundreds of dollars. He said, never mind, I'll just see my family later tonight. Then it turns out his flight was oversold, and so they were looking for volunteers to be bumped, and they put my brother on the earlier flight and paid him to go on the flight he asked to go on earlier. It was very fitting. But why are people bumped from airplanes? What must be happening if people are being bumped?
They're overbooking.
They're overbooked. Airplanes overbook. Why do they overbook?
In case somebody doesn't show up, they still have.
Yeah, and amazingly, large numbers of people either don't show up or they're on a plane that's delayed and they don't get there in time and then they have to take a later flight. And so the airlines have learned that for the most part, it's worthwhile to overbook And occasionally you just pay off people, and you give them some additional compensation. You know, some airlines don't handle this well. I can't remember if it was United, but they actually physically removed somebody who, was it United?
Yeah.
They physically removed somebody who was already sitting on the plane so that a pilot could go on the plane to fly to a place that was like a 2.5-hour drive away to be ready to fly another flight. And once the guy is already on the plane, that's a bad time to tell him to get off. You do this before they get on. It was terrible publicity for the airline. They're probably happy that I'm not 100% sure that it was United, but it feels like a United story. But you want to do these calculations and estimate how much money are you risking not earning by insisting that we only sell the number of seats available. And the airlines have done the calculations. It's worthwhile to occasionally give people these bonuses. But you need to estimate how much things are worth. This is why we care so much about these series expansions. And you can often interpret it as main term, secondary, the main term is a half. And as we get further and further away, this tells us the correction. And you hope you have something that's rapidly converging, so you don't need as many pieces. All right, this is probably a good place to stop. Any other questions? All right, so Monday will be the M&M's lecture.